So I'm going to talk to you today about a pretty straight-up tectonic application for Argon 4039 dating related to some research I've done in southeastern Mongolia. And it's a story about Phanerozoic continental growth, collisional orogenesis, and interplate deformation. I'm going to tell you sort of the excerpts that Argon speaks to. In terms of deciding to do this talk for this project, I went back and looked at the Earth scope goals and found things that I felt my research related to. And so this research in Mongolia really talks to factors that may control the location of interplate seismicity, and sort of how the tectonic evolution of a region may control the locus of deformation during subsequent tectonic events. So our area today is the East Gobi Fault Zone in southeastern Mongolia, and the fault zone you can see in the Stygial elevation model from GeoMap app is that green region, sort of a low subtle basin developed in that region. This map here is 1 century of seismicity in Mongolia, current to 2000. I would argue that already this is a little bit surprising to some people because we're really in a well-positioned interplate deformation, and there's quite a bit of deformation and large earthquakes going on in this region today, in part driven by the collision of India with Asia, but the Pacific plate boundary may also be moderating some of this deformation that we see. If we had a map of 200 million years of interplate seismicity, I would argue that we would see, a large cluster of epicenters here in the southeast of Mongolia. There is some modern faulting going on out there today, but I think it's sort of the orientation of this shear zone or fault zone I'll be talking about is not favorably oriented at the moment. But there's a severe history of polyphase deformation since the end of the Paleozoic. So a very simplified map of southeastern Mongolia. Again, this East Gobi Fault Zone runs up and down this corridor. And basically, this region is part of the Central Asian orogenic belt that is, part of the nucleus of the growth of Asia throughout the Paleozoic. And so a little schematic diagram of sort of how this region came to be. We're sandwiched between the Siberian and the North China cratons, but there are probably analogs out here similar to the western United States, Southwest Pacific tectonics, in the sense that there may have been several microplates, in the region of what is referred to as the Paleo-Asian Ocean, and our East Gobi Fault Zone may be related to the position of a suture between some of these microcontinental blocks. But the colors shown down here in pink relate to pre-Archean through Precambrian rocks of the North China craton. The colors in purple are Paleozoic arc rocks here, and the colors in green are Permian, sedimentary, and volcanic rocks that were deposited in this Paleo-Asian Ocean and are now sandwiched between the North China and the South Mongolia arc. So North China, South Mongolia arc, basically up here. And again, it's possible that there were some intervening arcs that collided. Following the closure of this ocean, there are some Triassic-Jurassic plutonic rocks that punch through. The Mesozoic history is dominated by Jurassic through Cretaceous rift basin strata, and an upper Cretaceous sequence that you'll see some images of. There's Paleogene strata, et cetera. But the timing of the closure, or the last presence of that Paleo-Asian Ocean, is timed in part from sediment, basin analysis studies in southernmost Mongolia and also in the southeastern part. So looking at the stratigraphy and this transition from marine to non-marine rocks. And in the terrestrial sediments, there's a dike swarm that cuts it. Some of these occur as sills. And argon ages from the volcanic rocks and the sills basically, give us a minimum age for the, confused. The basin had closed by 245 plus or minus 1.8 million years. So that's kind of the early Triassic where basically the collision has occurred at that point. And we're going to go up here into the northern part of the fault zone where we see more defined exposures of some of the basin rocks that give us a hint of the Mesozoic action of this region. This is an image of an unconformity between lower Cretaceous and upper Cretaceous strata. It's a regionally developed unconformity. It's an important time marker in the region and a strain marker in the region. These are rift-related strata, and these rocks are famous in part because they house basically the famous Mongolian dinosaur fossils out there. Working with basin analysis people who have again done the stratigraphy in the basins. We've dated volcanic intervals in the basins, late Jurassic pyroclastic surge deposits, and this is a petrified trunk of a tree out in the basin, and some volcanic intervals in these fluvial Dataic and lacustrine successions with early Cretaceous Argon ages. Again, kind of give us the timing of these sediments, and this basically lacustrine section becomes an important time and offset marker in the theme of our interplate deformation. So, that's some basic stratigraphic framework for this work. We're going to spend our time looking at basement rocks exposed in basement blocks in the northeastern part of this fault zone. I'll highlight that the rocks, in part, that we're looking at were largely mapped as Precambrian because of their high-grade, high-strain appearance and with no radiometric dates at all. So our Argon data are going to give us some insight into what the age of these basement rocks really are and the timing of deformation preserved there. So we're now looking at the Tavan basement blocks, so basement rocks in the Cretaceous, early Cretaceous and younger rift sediments out here on the margins. We're going to zoom in again to the northern Tavan basement block and see some higher resolution satellite images here. So this is the benefit of working in the desert. Not much vegetation and great Google Earth imagery, but these are the rocks that are again basically mapped on their appearance as being Precambrian in age. In some cases you can see, you can definitely see the structural grain in these rocks, and you can see where there is some onlap of these lower Cretaceous strata. Taking kind of a tour through these potentially or not Precambrian rocks, we have migmatites and amphibolite facies gneisses. Some rocks are more deformed than others. Obviously, there are synkinematic intrusions and, basically dikes that are cross-country that have been fed by leucosomes out in this region. And there are also some very high-strain myelinites that also basically cut across the migmatites and the amphibolite facies gneisses, become more dominant as you move off to the north. And in some thin sections from the northern part of the terrain, it actually looks like you preserve lithic fragments and, basically evidence that these were volcaniclastic sediments. We're starting to think more that we're looking at a crustal section going from deeper crust to higher crustal levels as you move north across the basement blocks. Looking at the structures in these rocks, again, from the satellite imagery, you can see this basic northeast trending foliation. It's true in the migmatite rocks. It's true in the amphibolite facies gneisses and also in the myelinitic rocks as well. And tough to see in this image, but there are some large-scale isoclinal folds in this region that show up both in the field and in the satellite imagery. So now if we look at the Argon ages from the migmatites, gneisses and myelinites and some of the synkinematic intrusions, our oldest ages, and again, these are all step heating experiments on mineral separates. So we have, for example, step heat experiments on amphiboles from metatextites. And you can see that there is, serially increasing ages as the temperature of the step heat experiment increases, but we achieve this plateau. These are 2 sigma errors that are quoted. So from the migmatites, we are getting ages from amphibole about 240 million years. A thin section, so a classic sort of gneissic, in many places granoblastic texture. This is actually some pilot titanite data that was collected at the UCSB lab, but and there's a range of ages coming out of this rock, but there appears to be potentially a population with an age that is roughly concordant with the amphibole date. This is from another section of the migmatites, so we've got another amphibole date from a melanosome, an age of 238, roughly concordant again with that 240 million year age that we saw in the previous sample. We looked at the leucosome and dated the biotite, pretty close to a 230 million year age. Again, this sort of argon loss type spectrum with a younger age in the lower temperature steps. This rock is a bit more deformed. You can see evidence for things like grain boundary migration, which is speaking to some deformation at temperatures in the 500 to 600 degree interval. And looking at the microstructures becomes important when trying to interpret the argon ages, because one thing you would want to ask yourself is, are these ages that I'm getting, are they purely cooling ages, or are they potentially dating the timing of deformation? So that's something in ideal, we'll revisit. If we look at some of the gneisses, so this is a amphibolite facies gneiss where amphibole is defining the mineral stretching lineation in this rock. There are kinematic indicators for sinistral shear here. Again, microstructure speaking to deformation at amphibolite facies conditions. And here we get an amphibole plateau age of about 225 million years. Again, with some argon loss, the spectrum is a bit complicated, but this loss theme persists throughout these samples. Biotite gives us an age of about 199 million years for the plateau segment, but again, some extreme argon loss with Cenozoic minimum ages. And here's the potassium feldspar age. This is a sample from, it's a very, felsic rock with large feldspar sigma class that again shows sinistral shear sense out there. The microstructures, again, basically show high temperature deformation. If you look at some of the feldspars in thin section, they're basically some core mantle structures, which again speak to deformation around 550 degrees C, or roughly in that ballpark. There's an SC fabric there, and we can see some of our mica grains both in the S and the shear planes. If we look at a biotite age from this rock, we've got a plateau portion of the spectrum that gives us an age of about 224 million years, again with this argon loss profile. We do have some zircon ages from some of these rocks, and I'm not showing all of them, again collected in the UCSB lab. This rock basically has a population of zircons with relatively concordant ages that may testify to its Paleozoic protolith. But again, the argon data are basically late Triassic in this case. If we look at some examples of some of the synkinematic intrusions, and it used to be that we thought this maybe was one big Pluton, looking at Google Earth 10 years ago. As the resolution has increased and we've done depth marches up and down across this region at 120 degree heat where you trade water in your pack for rocks, it's really quite a mix out here of these migmatites and amphibolite facies gneisses. So the structure is much more complex. There's another sort of leucocratic looking region out here. So from this region out here, one of our older ages, from an amphibole, a plateau around 223 million years. Fairly straightforward. The feldspar from this rock has a flat-like segment, but it clearly has a memory of past life or past gas, as you want to call it. Bad pun for the end of the day. If we look at, this is a synkinematic intrusion. This basically this leucocratic intrusion here is less deformed than some of the gneissic rocks around it, but does have some foliation development and folding in it. It's kind of a complicated sample in terms of its zircon populations, and it appears that there may be as many as 2 late Triassic zircon populations, one giving intercept or, the concordant ages, again, roughly around 225 million years, a younger population around 217 million years. But, we're getting, again, ages from zircons that are roughly concordant with amphibole ages from these rocks. If we look at another suite of mylonites out here, and it may be that this is a later shear zone that has developed and perhaps offset this segment of rocks from these over here. Again, nice myelinitic fabrics, another SC fabric, more feldspars with these sort of core mantle textures, again speaking to deformation at relatively high temperatures. And also the idea that these microfabrics are frozen in. So again, the integration of looking at the microfabrics with the ages in terms of interpretation, and just while we're looking at this one, if this rock sat for many millions of years at 500 degrees C statically, much of this would be recrystallized with polygonal quartz textures, etc. But we are preserving the quartz microstructures, etc. So this myelinite, we dated both white mica and biotite, got plateau-like segments that are basically concordant and around 212 million years, again with a small bit of argon loss. There are cross-cutting dikes that in the field, well, they're somewhat complicated, but others that look relatively undeformed. If you look at them in thin section, they do preserve some evidence for minor deformation. Here, a biotite from one of these cross-cutting dikes gives a plateau-like segment, 214 million years. The K-spar spectrum is a bit more complicated, but similar to some of the others, at the lower temperature steps, basically locking in ages at around 180 million years. If we take these ages and try and look at them in a temperature time type of framework, again, more in terms of the thermochronology, so these are all ages from Tavan Har, including the zircon and the titanite. So we've got error bars related to our 2 sigma errors on the age, but also we don't know exactly what those closure temperatures are. We can see that these rocks have basically spent some time probably in the lower middle crust environment, and based on data I haven't shown, I would argue that preceding this, probably since the end of the Paleozoic, they resided in this sort of regime. But you can see there's a clear trend from these older ages going on up to, again, late Triassic ages ranging from 225, concordant with those amphiboles, on down to about 214 million years for both the mylonites and the syn to post-kinematic intrusions. And I've hesitated to basically, draw the paths, but these rocks basically have to go from this temperature to that temperature in that time interval. Here we show basically the trajectories of different cooling paths, so 40 degrees C per million years, 20, 10, 5. And in some cases, these rocks are clearly cooling very rapidly. Again, the kinematics of this late Triassic deformation based on the ages are sinistral according to things we've seen both in thin section and in outcrop, which is a little way surprising because for pure strike slip you wouldn't predict exhumation or cooling necessarily, but I think there is potentially a transtensional component to this deformation, which may, basically aid in exhumation, relatively rapid exhumation in the late Triassic. And I tried to model the feldspars, the thermal histories. That's something we haven't been able to talk about today due to time, but they're the Lovera models for cooling histories of feldspar can basically give you information on cooling from about 300 to 150 degrees C. Our feldspars here are textually complex. They've also had a tortured life post their ductile deformation. So the models didn't work out, but I plotted basically maximum and minimum ages from the spectrum. And we do have uranium, thorium, helium, and apatite fission tract data from here that I haven't been able to show, but that's what goes into these hefty models showing the lowest temperature cooling history. So we potentially have Paleozoic protoliths that have undergone partial melting, and maybe in the early Triassic. Again, that would be a minimum age for that. Clearly, I think, evidence for a strong deformation episode in the late Triassic at amphibolite facies conditions that brought these rocks up probably to, the base or near the brittle ductile transition where they sat and then eventually reached the surface during later tectonic episodes. These are all the data I've shown, but the majority of the data, I didn't make a new plot, but again, our migmatite ages, our sinistral shear zone, here are some of the cooling ages from the feldspars, and again, all this argon loss, which you could ask, is that thermally activated, diffusion-related argon loss, or is it somehow related to a brittle deformation overprint? And I would argue that we're dealing in these samples with brittle deformation, that events that are reflected in some cases by the minimum ages on these spectrum. Because if we go to the margins of the basement blocks where we've worked, we see, fault zones related to the rift basin bounding faults of the late Jurassic to early Cretaceous basins. There's evidence in the rocks for a basin inversion event around 100 million years ago. And there are also later stage, tertiary, we think, in age, sinistral strike-slip faults that deform this region. And it turns out the Cenozoic strike-slip faults basically have the same northeast trend as the late Triassic, the migmatites and the late Triassic sinistral shear zone. So we think that these basement blocks are basically crustal boudinage that are exposed in the midst of these basins that have a pretty severe polyphase tectonic history. Back to these green rocks, these were originally proposed as offset markers, which the work of Human et al. Has proven based on some detrital zircon data and other factors. These are Paleozoic rocks again, so if they mark, sinistral offset, they're sort of a total increment of offset. It turns out that we can use some of those early Cretaceous lacustrine rocks as a secondary offset marker that postdates the late Triassic shear zone. And so in total, across this East Gobi fault zone, we have several hundred kilometers of offset. The majority of that appears to be late Triassic in age, and about 100 kilometers of that is Cenozoic based on the offset of the lacustrine rocks. You probably can't read this down here, but we tried to look at the timing of these events, and basically there is good overlap between different events related to Pacific flat slab subduction, the North China, South China block collision, the West Philippine block collision, et cetera, with some of these different events. So Mongolia is basically responding to the building up of the Asian continent throughout the Mesozoic and Cenozoic. So the partial melting may have been related to the closure of the Paleo-Asian Ocean, the collision of North China with the South Mongolia block. The EGFC may have been a synccollisional strike-slip fault, and perhaps again, locus, overprinting a Paleozoic suture, time will tell, maybe with some more geophysical work, if it gets done out there. But, we basically have this locus of polyphase deformation in this heterogeneous collage. And so I think, again, these rocks are basically telling a story of the building up of a continent and then the interplate deformation history as a result of far-field forces going on in subsequent eons, perhaps. So I'll leave it there and take any questions.